everybody. So today I'm going to talk about timeouts. Timeouts, you cannot trust them just because they give you misconceptions. It's sort of like how this is called the green room, but it's not green, right? But you keep believing that it's the green room. So it's mostly based on my experience working at Twitter. So let me just tell you a little bit of story. So this is a very famous, at least at Twitter, this is a very famous tweet coming from 2014 Oscars, where Ellen called her followers to retweet and favorite this tweet as much as possible. While I do not believe that this is the best photo ever, this was the tweet of the year in 2014 for Twitter. And for anybody who was actually on call that night, they remembered it as the tweet that caused a spectacular incident that kept everybody busy for the next several months. So as much as Ellen wants to believe that she single-handedly brought down Twitter, I think the reality is she started it. She had very enthusiastic followers who participated well. But quickly, the whole play out got taken over by retries, timeouts, and all those mechanisms in our data centers that were supposed to prevent bad things from happening. And in the center of that storm was actually cache. This brought us to who I am. So I was working on cache at Twitter for 6 and some years. So I've been there for 7 years, and for the majority of that time, I was working on cache. So that made me a dinosaur, especially by Silicon Valley standards. Now I have carried the spirit of cache onto my new team, which is working on performance in general. But cache is an interesting example because it's such a simple in concept, but critical in terms of performance piece. So allowed me to observe a lot of the distributed system behaviors just at play at very high scale. So why do I want to give this talk? You see, for a number of years, I was on cache, and that means I was on call for cache for all those years. So every time something happens, and inevitably the things that matter use cache, right? So someone would observe that their cache request started timing out, and their retry kicked in, and they say, oh, the cache is not behaving quite well. Let's page the cache on call. So often I got woken up in the middle of the night, and I had to look at a bunch of dashboards, and I say, you know what? I don't think this is cache. So if anybody watches House MD, it happened about as much as when they say it's not lupus, right? And it's never lupus, except when it is. It's like once or twice. So you can imagine when I go to the incident room or the chat room telling people, it's not my fault. They're not the happiest about it. So they kept pressing. They say, OK, if it's not cache, why are my cache requests timing out? Why am I retrying cache requests? You've got to have an explanation for this. And if you think it's something else, tell us what that thing is, right? So that's when I started actually looking at other people's code, because I realized this will keep happening if I don't tell them exactly what's going on. So I did that for a number of years. And after telling about 20 or 30 or who knows how many teams that this is happening, I realized, you know what, maybe it's not just this 1 or 2 or 3. Maybe it's worth telling more people about what actually happened if you see behavior like that. And the reason I'm here at the conference called YOW is it's literally calling my name. So when I got an invitation, I'm like, I have to come here. To my knowledge, I'm the first YOW speaking at YOW, so very proud. So what do I know? So I think you need to know my limitations to sort of take the right message away. I've only really worked on cache in any kind of depth. So that really shapes my view. If you have a system that's very, very different, it may behave differently, so this may not matter as much. And the other thing to note is I have been working on Twitter's environment, which may have some similarities to what you're familiar with, but maybe not. So let's look a little bit closely at what I mean by those two things. First is, what is cache in data centers? So caching in data center really is just very large distributed in-memory key value store. And the operations is extremely simple. You send a TCP, you create a connection, send a request in some very cheap to encode format, and you get a response back. And the catch here really is we're serving many, many requests at a given time. So I'm talking about single cluster serving tens of millions of requests per second, or collectively hundreds of millions of requests per second. So to give you an idea of the scale. We can do this because it's really dumb, right? I'm not trying to say I'm working on super fancy stuff. It's very simple. The other thing is it has very tight latency expectations. People do expect cache requests to come back usually under a millisecond, but in the worst cases, only a few milliseconds or tens of milliseconds, right? So this means that there's much less room for all kinds of weird things. So what does Twitter's environment mean? Twitter's environment went through architectural changes where we started with Ruby on Rails, which we call the monorail, and then get broken down into SOA. And today, everybody wants to say that's called microservices. We'll come to that later. And because we own data centers, there's a lot of things we can do, right? We have access to physical hardware. And Twitter is known as a Scala shop. But in reality, we have both Java and Scala. The commonality is most of the heavy lifting happens on top of JVM. So if you don't have JVM, things may be different. And we have been very aggressively moved to a containerized environment. So our container solution of choice is Aurora Mesos. I think Kubernetes actually share a lot of the same constraint when it comes to resources. And in terms of scale, what I have seen is, thousands of nodes per service, maybe 10,000, but that's the largest we have. So to give you an idea of scale. So let's take a step back and see why we are talking about timeouts altogether, right? It's a very short intro, don't worry about it. So I think it boils down to the real world is not perfect. In the 70s, there were papers and there were discussions about what is formalized as too general problem. What it actually says is essentially you cannot have consensus over links that are unreliable. So theoretically, the system can end in any state. It's just not going to be happy. But that did not stop engineers. Engineers say, theoretically, we're not going to reach a consensus, but that doesn't matter. In practice, we can get to very, very close to the ideal. And the way they do that is they use a timer. Say, I will bond my attempt by this amount of time. If things don't work out, I'll do it again. So this gives us retries. And of course, the failure could happen on either direction of the communication. So in this case, it doesn't make a difference for the person on the left. She will still retry upon the time of firing. And there are other systems in which you would just proactively send out many messages and hoping the majority of them or some number of them will come back. And this is known as quorum. It's not used super well because sending a lot of requests instead of one and wait is a lot more costly. So really, that's the essence of the engineering approach to this problem of imperfect communication is timeout and retry, and that's why we're talking about it. And finally, because a lot of us run services here, nothing is done only once. You keep doing the same thing over and over again. So if you have tried the same request a bunch of times and the remote service doesn't seem to be responding, you decide that you need to do something smarter, right? Instead of trying to beat the dead horse, maybe you should go to someone else. Or maybe you just give up altogether, say, I cannot do this right now. You return a 404, return a 500, whatnot, and just live with it. So we have timeouts, we have retries, and we sometimes take more sort of larger scale actions as our mechanisms to coping with failure in distributed systems. And anybody who has worked on large-scale distributed systems know that the business logic, you can hack a prototype doing something cool in a very short amount of time. To bring that system to production is actually the vast majority of the work. So the complexity of distributed systems, some say, is mostly in the edge cases or failure handling cases. And a different variation of that quote would be the first 90% of the project takes 90% of the time, and the last 10% of the project also takes 90% of the time. Right? So this gives you, that tells you a lot about how tricky and difficult it is to get the failure cases ironed out. So just to, I just want to make sure everybody has sort of a mental model of how this is usually seen. Right? You have a request, you usually go to a remote service. You have a timer, and you usually want to retry because you intuitively know that if you try it again, it may succeed, so improve your overall success rate. And if the result from that is unsatisfactory, you may or may not decide to do something else to prevent future failures from happening. Right? So this is the sort of a very intuitive, naive failure handling model that a lot of engineers would keep in mind. So how do we characterize these mechanisms? I think there are certain things that sort of stood out and is worth mentioning. First, because there's no way of getting a perfect knowledge of the communication over a link, timeout is merely approximation, right? So I feel like people know this in theory, they often forget about it in practice, is that when you say something has timed out, you're calling it a failure, and it may or may not actually have failed. So the thing to know, to remember about timeouts is when you have a timeout, there is a chance of false positive. So the request may be just perfectly fine, you just have a timeout that's too short or something that's not expected, so on and so forth. And the thing about retry is an effort. That means your service is actually doing work. This work is something that you may or may not have budgeted for because maybe normally you don't need it, right? So, and the other thing that is even less obvious is retry often changes the state of the system. So we'll come back to that later, because but this is important because when you have a system and it's in retry and it's in a different state, whatever benchmarking or testing or reasoning you do for the normal state may not apply. The characteristics of the system may change. So you may not get the same behavior if the state is different. Finally, failure prevention, I would characterize it as an escalation, meaning that if you made a good decision, you are now making a good decision for a bigger system. If you made a bad decision, there's also a chance that you are bringing that bad decision to your entire system. Right? So it can go either way. So I think what we have seen, at least in our production, is with regard to these mechanisms is what works intuitively, what works in our mind, or what works when we are doing small local tests, often ends up leading to catastrophic outcomes, as in the case of the Oscar tweet. So why exactly is that happening this way? First, let's look at timeouts. Timeout is, in this illustration, timeout it shows as something happening in the middle, right? So that's how a lot of people perceive it, is communication has been interrupted between these two services. So I think one of the common misconceptions is timeout informs us about the communication to remote services. But is that always true? That requires a deeper look at the sort of close-up look at what a modern service means. A modern service doesn't run on bare metal, like almost never runs on bare metal just by itself. It runs on a very deep stack, right? You have your service application logic on the top. You may be using a number of libraries. You may be running on a virtual machine. By virtual machine, I mean JVM or other language VMs. And then it will run on the operating system, will run on the kernel, and then it runs on physical hardware, and underneath it you have your shared network infrastructure in the data center. And if you scale this out to look at the service that's locally, that's the service you care about, that's your service, and the service that you are talking to, I think the construct is often symmetrical. So you have very deep stack on both the local side and the remote side. And for the discussion of, for this discussion, we actually don't care so much about the remote side because if the remote stack is screwed, I don't really care where the error happens. I would just consider the remote service being bad, and I would do something about it, right? But the interesting thing here is, for your service, you live on this very deep stack, and there's nothing you can do about it, right? You cannot say, I don't like the kernel that I'm currently running on. Apparently it's doing something stupid. I'm just going to swap it out and get a better kernel, right? I have heard of sort of failure prevention mechanisms where you would a service would just kill itself, hoping that you'll move to somewhere else, but I don't think that's a common practice. Most people don't do that. So this basically is the family that you're born into, and then you can never get out. So if you have a request, it has to traverse this very deep stack, go to the remote service, and come back. And if you have a timer, chances are that your timer is at the very top. And you're measuring this whole trip, not just the part that's spent on network, not just the part that's spent on the remote service. And there are so many things that could go wrong in that stack. Oh boy. So say you have an application. Is there anywhere where resource can be contended, like a queue that has a shared lock, or some head of blocking if things are processed in order? If you use libraries, do you ever call malloc? Malloc actually has indeterministic completion time, right? It can be very, very fast if it comes from thread local store memory. It can be very slow if it goes all the way to the kernel, get a new page, do some paging. So a lot of things could happen. And when it comes down to kernel, the kernel does not only support your application. It also needs to handle interrupts, do I/O, all those things that are completely out of your control, also completely out of your view. And when it comes to hardware, there's blocking I/O again, there's congestion on the network potentially, and there's cycle stealing. I have years ago, there was an amazing incident in which it turns out the firmware on the server that we're using are actually stopping all the CPUs in our server, with no good reason. So you will see the server basically frozen for a number of seconds without doing anything. And the kernel cannot tell you anything because the kernel is entirely stopped. And this is all done by the firmware that's sort of underneath the kernel, right? So all these complexities are completely hidden away from modern developers. And of course, there's the network. You can drop a packet, the deep queue can overflow, it can have significant delay, all those things. So there's the deep stack. But things get even more interesting when you are on a multi-tenant host. This is true if you are inside a container and co-owning or co-living in a hardware with multiple containers. So you have no visibility into anything anybody else is doing. But all these services still share the underlying kernel and underlying hardware. And unless you have your own VM, the protection between these services are actually not that great, right? So everybody knows that in a multi-tenant environment, your service is the good one, everybody else is potentially bad. And what do they do? They steal. They steal your cycles. And you're like, no, it's a container. I have my assurances of these are the two CPUs that are mine, and these are the memory that are mine. Someone is going to enforce the policy. Yes, but if you look carefully at how that policy is enforced, the guarantees are not as good as you think, right? So for example, both Kubernetes and Mesos use cgroup to enforce CPU quota. So you are, in the long run, supposed to get the fair share that you declared. But cgroup CPU policies are enforced by the scheduler every 100 milliseconds. So someone can swoop in and steal all the cycles for the 100 milliseconds. Now they will be punished. They shove it in the corner and probably stay there for five cycles, and they can come back out. But during those 100 milliseconds, you are punished. So your stuff is not running. Someone else is stealing your cycle. And 100 milliseconds in a data center is an incredibly long amount of time. The typical end-to-end round trip in a single data center is well under 1 millisecond, right? It's on the order of 400, 500 microseconds. So you can send 200 requests back and forth in an ideal condition by the time you are freed from this prison, which is cgroup. So just keep that in mind that actually multi-tenancy makes things a lot worse. And then we have this, what I call timeout cascade. It's fun. This is a little sort of, there are a lot of pieces on this. But essentially, it's what happens when you have dependencies that goes more than one step. Right? So the first RPC call will go from service A to service B. It will wait in some queue. That's inevitable. There's network queue. There's TCP socket buffer, et cetera, where time is basically unaccounted for. You don't even know that exists. And then you need to do some preparation, computation to handle this request. And then you may send out another RPC request for the second dependency. And here, what happens in real life is often time spent in the first two steps are not really carefully tracked. So people have no visibility into how long it takes before they even see the requests. And that contributes to some of the misconceptions about timeout as well. So to put things about timeout together, so the unfortunate truth is that timeouts often do not indicate the health of remote service, even though people sort of seem to assume that because that's the natural thing to do. And the optimal timeout is sort of a moving target because if your environment changes, often things sort of get pulled out from under your feet, right? There's not much you can do about it. So the characterization of that environment might change over time. And if you live in a shared environment, which is very cost efficient, you have to deal with all these aspects that makes your runtime much less predictable. And if you try to have a global view of where you spend time, there are all these gaps where there's basically no light shone into, and you have black holes in your timeline. So here is a sort of a practical exercise. Say we have a chain dependency, not too complicated, just A, B, C. And A's requests are timing out, but not B's. Let's say you're in the control tower. You get to page don't calls for any of the service owners. Who should you page? Well, in this case, actually, I think C usually does not get paged, right? So it's clear that C is actually returning requests to B. But between A and B, either of them can be at fault, right? So it could be either A or B or both of them. So what the control tower would do is they would page both of them. All right, so that's an easy round. Now, A and B are both timing out. Who should you page? So now, so if you just look at B and C, you get the same conclusion. It could be either B or C or B and C. Now you just add A to that formula. You get basically all the combinations, right? It can be AC, AB, ABC, BC, or B or C. Like at that point, the person on course like, I don't know. Like, fuck it, I'll just call everybody. So that's how I ended up in the room every time, right? I'm the C here, and if B is timing out, I can almost be sure that I will be there because nobody can figure out what's going on. So that's just one chain. Now, modern application architecture is a wonderful place where you will have a mesh of dependencies, right? That's the promise of the microservice architecture or SOA architecture is you can have all these services independently evolve, and you can just call your dependencies when you need to, and you often end up with a mess. And if you think that spaghetti is bad, this is an actual sort of dependency or call chart graph of Twitter. And I stole this picture from Katie's slides, she spoke at YOW last year. So if you go look at the archive, this was in her slides as well. So compared to this, the spaghetti actually didn't look so bad, did it? So what does it mean? It means, I'm pushing the wrong button here. So I think a lot of people, I think this has been drilled into scientists over a number of years, saying correlation does not equal to causality. So what I think should happen for distributed systems engineers is sort of just repeat this to yourself every time something like this happens, is timeout does not equal to causality. If you want to figure out what causes what, you really need to find the signal somewhere else. All right, so that's timeout. Now let's talk about retry. Unfortunately, it doesn't really get better It's going to get worse. So we still have our mental model. And the intuitive understanding is retries improve the success rate of my service because the first time it failed, the second time it may not, right? This is true if the failures are actually entirely independent and you start from the same place. And neither of these two assumptions are necessarily true in your production system. So what ends up happening is, so there are few things to consider. First, we said retries extra work, right? So clearly the person sending the request needs to do twice as much work, if not more, if they want to do the same request twice. And if the communication is sort of sabotaged on the way back, now both sides need to do twice as much work, right? So that's number one. Number two, retry doesn't even equal to replay. It's not the same thing twice, unlike the simple illustration. Potentially, you actually change the behavior. So it's very common, for example, when you have an RPC timeout to say, I'm going to close the connection because I have no idea at this point what data is in the pipe, right? So I'm going to have a clean slate. So now you're reopening a new connection. And opening a connection is actually work, right? So that's not the same as just sending a request over an existing connection. The other thing is the state has changed. OK, so you have a new connection, new object. Guess what? You have more garbage if you are running on top of a JVM. And there's also hidden retries in the lower stack, TCP retries. Nobody ever thinks about it. So you think you're doing one retry at the top. It could be 3 packets going out on the wire. Right? So all these things are happening without everybody noticing. And also retry is not as simple a decision as timeouts. Timeouts, you have one number. That's pretty much it. Retry, you need to consider how many times do you retry, and how do you set the timeout for subsequent retries, how much do you wait between retries, and how do you write the retry logic exactly, because it can be different, and where do you go, because you may not go to the original service. So all these are fiddly tuning knobs that you need to be aware of. So finally, let's say for retries, it is extra work, and therefore it can create a positive feedback loop where you're loading an overloaded system. And it can change the system behavior, and it can change the system state. So you're looking at an entirely different service from the one you are familiar with in steady state. And to configure retry in a sophisticated way actually has to deal with a lot of parameters. So if you have chained dependencies, here's another fun sort of exercise. Well, I guess the answer is given out already. So if C is slow, it's straightforward, right? B would time out, and B would retry. And if you don't set your timeout for A correctly, B timing out could actually result in A timing out as well. So A decides to retry. So now you suddenly have 4 times as much traffic to a service that's overloaded. And if B is slow, things actually can look strikingly similar to if C is slow, right? B is slow, and therefore B times out. B says, oh, C must be bad. So it does twice as much work trying to send more requests to C. And of course, because B is slow, A is going to time out. You still end up 4 times with 4 times as much traffic to C. So otherwise would-be healthy service can be dragged into oblivion, even if something just depends on it is slow. So now we can talk about the famous incident. I think it was interesting because it basically was a perfect storm to facilitate this kind of positive feedback loop. Let's look at what those conditions were. So first, when we have timeouts, at the time we decided we want to tear down the connection and have a clean start, right? And the second thing is we have a large number of clients. You can imagine the service responsible for tweet would be one of the more prominent services at Twitter. And each one of these clients actually have multiple connections and a variable number of connections to cache because the load can go up and down. And we have a full connectivity mesh because we don't want the middleman. It's cheaper to run that way, so every front end just talks to every cache. And finally, we already moved on to container-based deploy, so everything is run on container and subject to the C group rules that I talked about earlier. So the event went out as this. So Alan, successfully introduced a hotspot on one of the cache backends. And of course, that cache backend is going to be a little slower. So there's timeout happening on the client for that particular tweet. So what they do is they say, oh, let's clean up these connections. And then you have an initial connect storm, right? So they still want the tweet, they will reconnect and resend the request. Now you have a lot of outstanding connection requests to the same host. And connecting turns out to be actually more expensive than the actual requests themselves. So now you have even more timeouts. Now, because we have a full mesh, the timeouts is going to affect every single front-end server trying to talk to cache. And then you get more clients doing the same thing. We end up with a bigger storm. And in the end, the NIC is saturated with just TCP sync packets. That's when we declare bankruptcy. So you can see that in a service mesh, the top level retries really have a lot of power, right? You can trigger a lot of work deeper down the stack. And the lower you are in the stack, actually there a bigger multiplier that potentially could be if the timeouts tend to compound. And it's very hard to predict where the original bottleneck is because things are connected in such a way that anywhere, either side of the link could be the cause, and the cause can propagate to other parts. So reasoning about it is really hard. So after all that, we still want to do more. We want to prevent failures from affecting future requests. So I'm not going to spend too much time here because how people do failure prevention actually is highly service specific, right? So the way you prevent future failures for a stateful service would be very different from a stateless service. But what tends to happen is you have a bit of information, you try to make a decision on behalf of the entire system with the information you have. So there's always the possibility of propagating what is local failure to global. If you only act on a local information, you can make what would otherwise be a transit failure, if you think that's severe enough, you can promote that to be a global failure. So you now are actually making things worse for a longer time. And if you make failure prevention decisions on local nodes individually, they may end up in different places, causing inconsistency in the entire system. So none of the intuitive understandings of the failure coping mechanisms are actually true if you look at them closely. And I think this is so because fundamentally it's because of the limitations of very little input, as well as having your logic actually dominated by a single feedback loop that is prone to becoming a positive feedback loop, right? So if you are familiar with systems theory, then it's actually inevitable that if you only have one loop in your system, that loop can sometimes dominate the behavior. And you can only reach equilibrium when you have multiple loops that are sort of constraining each other. So really, this is where we want to be, is we want to bring in more information, and we want to bring in more different mechanisms into our system. So I think we should always start with what I would call the baseline. So understand what's the reality if you run services in data centers, right? I'm not saying you're not looking at this. I'm actually fairly confident that everybody in this room already knows what it's like to have a machine going down, what it's like to have a rack going down. But what people don't think about often is, are there things that happen just as often as machine going down, or more often? For example, do you GC? You probably GC way more than services going down. Have you ever characterized the behavior of GC? How much do you get frozen or hold up because of GC? How much does some kernel background task run every time? And how often does it run? Does it happen more or less than hardware failure? So a lot of times those things happen way more often, but people don't look at it because these are the sort of commonly known failures. But I think these are great baselines. So if you're considering these events, you should definitely consider events that happen even more often. So the other thing is, so if you have a common understanding of what are the common events, then you're on a good footing for building good timeouts. So I think for good timeouts, the goal really is to minimize the chance of having false positives, which means we actually need to look down and see what's the behavior of the library, what's the behavior of the kernel, what's the behavior of the hardware. and know how long all these sort of anomalies take, and knowing that you cannot really avoid not talking to the layers that you depend on, then the timeouts should take care of those, right? You shouldn't punish a remote server if you know your local allocation is going to take, 20 milliseconds. You should tolerate that kind of behavior if it's local. And another thing is sort of, if possible, pulling other information to understand what's really going on. So most services say, oh, something happened and the request times out. I'm going to raise a timeout exception. If you think about it, it's kind of funny. Like, why is it not I just GC'd for 100 milliseconds, therefore things are slow exception? Why is it not, malloc actually returns super slowly this time exception? Like timeout exception is not very informative. And sometimes there are information readily available that helps you just understanding the nature of the failure better. I think this is something that was also mentioned in the talk earlier in this room, right, in the morning. So understanding what's going on is actually very, very powerful. And whenever possible, trace. So you have, I said timeouts does not equal to causality. So what does equal to causality? If you can trace the life cycle of when it goes out, when it comes in of a request, establish the timeline of a request, that actually tells you definitively what is the causal relationship between all these events. And if you are actually using microservices, I have bad news for you, because microservices actually makes this type of reasoning much harder. So as much as monolith is unwieldy and slow to develop, there are a lot of tools readily available if you want to reason about the events that's happening inside a single monolith. Once you leave the service boundary, often means you're leaving the user space or at least leaving the host that helps you reason about these things. So the visibility in the microservice architecture actually comes to you at a much higher cost. You need to put in actual effort into getting that visibility. And that's the aspect of the microservice architecture that I don't see mentioning very much, right? This bigger blind spot is not mentioned enough. And if you want to make retries better, so I would say just start from not copying someone else's configuration. This happens surprisingly often, right? My favorite service is using 3 retries. They must have a good reason for it. I will use three retries as well, right? So even just trying to understand why they use 3 retries and who are they talking to? Am I talking to the same service? Do I send the same amount of traffic? This is actually very, very close to the heart of distributed systems, is to understand this kind of behavior, right? So it's not really the thing you do the day before you launch to fill out this form about configuration. The configuration is important. And if you can, be more conservative instead of aggressive, right? So this is counterintuitive, because we think if we retry more, we have a better chance of succeed. But in reality is just do at the least amount of retrying you can to get the same success rate is better, because you are not feeding ammunition into that positive feedback loop as much. So finally, if there are rules that are not based on timeouts, there are rules that are based on the state of the system, whatever the state that is. Am I going into GC soon? Am I holding too many outstanding requests? Am I retrying too much in the recent past? These are the states that will help you determine the health. These will serve as brakes for the feedback loop, right? So if you have this kind of rules in place, you are much less likely to go over the top and over the edge of the cliff. So another thing is if you have dependency, it's good to always have have a global view on your dependencies. If you have a budget, start the budget from top. Even if there is this accountability gap where you don't know how the time is spent, having a budget and budget breakdown by your dependencies is better than not having that. And another thing is, if you can apply back pressure, definitely do it, because who knows better about a service that's under load than the service that's under load itself, right? If your remote service tells you it's under load, it must be true. So that's actually highly valuable information to have. But this is something I also don't see too much in modern protocol design, right? So there's a lot of remote procedure protocols. I would say a very large percentage of them actually don't have baked in back pressure mechanism. So next time if you're designing a protocol, you may consider adding back pressure as one of the default features. It may save you down the road and when you scale to a certain level. So in terms of failure prevention, again, there's nothing too specific, but the two things that worked out well, in my experience, has been, if you want to make a global decision, try not to act on local information only. Right? We definitely made this mistake in our own experience, and it often sort of escalates in the wrong way. And the other thing is sort of suppress the urge of, oh, I know something is wrong, I'm going to fix it for everybody, right? Just wait on it for a little bit longer. So you may ask, my system is suffering while I wait, what do I do? I think what could happen is you have a local mechanism that's fast in reacting, but is sort of short-lived in its effect. And you can have another global mechanism that is taking bigger strides, but will wait much longer and therefore be much surer about the global state of the service. Using a combination of these two generally will give you pretty good, reliable results. And finally, nothing can compare, sort of replace the value of testing. So for the first one, I think everybody knows about these things. You need to test everything. You need to test partial failures, and you need to test common failures often. But the last one is something, so originally what I said is you need to try test catastrophic scenarios, and I realized, no, that's stupid. Why would anybody introduce incidents to their services just on purpose, right? There's a good chance your service may fail. So I think one thing that would be interesting to test is you think you need this kind of retry policy or timeouts to get to a certain service level objective. Can you do the same with more relaxed timeouts and with more relaxed retry? Because again, this actually gives much less fuel to the potential feedback loop that can bite you in an incident. Right. So to basically give you an idea of what we are doing to the service that I owned is over the years, we put all these sort of insights and experiences into what we call a configuration guide for cache. That is only for one type of client, which is finagle memcache. That's the one that Twitter uses. But the guide alone is 2,000 words, not including all the sample code. So you need actually a lot of work put into doing this type of configuration properly. And our timeout is also fairly nuanced. Right? You can see we think we can do, we actually know, not we think, we tested that we can do 5 milliseconds at P999. But if you look at the timeout, that's super lenient. They're on the order of hundreds of milliseconds. Why? Because all our JVM applications can go into GC for that long. And also, the C group rules are enforced at a 100 millisecond interval. So it doesn't make any sense to do anything less than 100. So this is something that's quite counterintuitive to all the people using cache because they expect what's on the right, but actually they need to do what's on the left. And we have different retry policies for read and write, just because the syntax is different, the semantics is different, and the purpose is different, and we decided that we can actually protect the system better if we treat them differently, and they have different backoff, and there's also an overall retry budget to break the circuit, right, when we are retrying too much. And we have 2 levels of failure prevention. The local failure rule is fairly fast in engagement, but it only in effect for a short amount of time, and you can make a global decision by someone else in the system who is a third-party observer, and the change doesn't kick in until well after a minute. Right? So these, and for something as simple as cache, if you want to make it work actually somewhat reliably, you actually need to do a fairly sophisticated configuration. So I want to close by briefly mentioning something else we did, and that is not quite along the lines of configuring timeouts and retries, but at some point you realize that properly configuring timeouts and retries are just too hard. Right? That's often an indicator of you actually need to do something to reduce the variance and to improve the reliability of your system. Right? So So quickly, to give you an example of what we did with cache, we actually changed the application in a number of ways to remove some of the contentions, and we removed the blocking calls. And at the system level, we actually did a lot of sort of low-level tuning so we can rate limit the number of connections, and we're not on shared host because shared host simply was not doing good enough for us. And we are even setting CPU affinities so that we know the behavior of the kernel is a lot more deterministic. Right? So timeouts, retries get you very far, but when that becomes too hard, you know you have more interesting work to do to make the system behave in a more predictable way. So to close my talk, what I want to say is we know theoretically that perfection is not possible. And in practice, as engineers, I think we need to sort of internalize and just know that it's OK to fail sometimes, and it's OK to give up sometimes. And it's actually better to give up and fail in a deterministic way than retry and retry until we end up in catastrophe. Right? So if you understand what is the common behavior of your system, including dig down the stack that's not owned by you but where you depend on, and you can have a bigger picture about the health and the state of the service and act accordingly, introducing a second feedback loop to counteract the primary one, that's the one everybody understands, then you probably will be in a state where you are happy most of the time. And that's what happens to cache is we haven't got a single incident in the past year, knock on wood, that's not going to happen anytime soon. But so can it fail? Yes, it can. But compared to a few number of years ago, we're way better, right? And that's the result of all these exercises that we did just about configuration and just about understanding what's going on in our system. So that's everything I have. Thank you for listening. If you have any questions, I think we have 5 minutes.